For decades, computers represented words like this. Cat was the vector 001, 000. Kitten was 01000000. Banana was 000010. Now, quick question. Which of those three is cat most similar to? Mathematically, compute the distance. Ready. Cat is equally distant from kitten and banana. That is what our numeric representation of language looked like for 50 years. This is one-hot encoding. Each word gets its own dimension. Nothing about the numbers says anything about meaning. Then in 2003, Bengio and colleagues showed you could learn a smaller, denser vector for each word. The distances between vectors could carry meaning. That single shift eventually gave us modern NLP. Last video, I showed you the magic trick. Vector arithmetic in a word embedding space. King minus man plus woman lands on queen. Today we back up, because before you could do that trick, you had to solve a much more boring engineering problem. How do you actually turn a word into a good vector? And the answer took literally 50 years. The puzzle. If you want a computer to reason about words, you need a numeric representation. The obvious answer is give each word a unique ID. That's what NLP did from the 1950s until 2003. It worked-ish, but it had one fatal flaw. And that flaw is why every modern language model uses embeddings instead. Today's 3 beats. First, what one-hot encoding is, and why it dominated NLP for 50 years despite being obviously bad. Second, Bengio's 2003 shift, the neural probabilistic language model, first real embedding. Third, what distributed actually means, not just small, a specific mathematical property that changes everything. Beat 1. One-hot encoding. The simplest way to represent a word. Assign every word in your vocabulary a position. If your vocab has 50,000 words, each word gets a vector with 50,000 slots. The vector is all zeros, except a single one in the position for that word. Cat might be position 4200, kitten position 4201, banana position 92. One-hot has 2 fatal problems. First, every pair of different words is exactly the same distance apart. The dot product between 2 different one-hot vectors is always 0. Cat and kitten are as unrelated to a computer as cat and banana. Second, vectors are huge. 50,000 dimensional means every operation is 50,000 times slower than it needs to be. So why did NLP use one-hot for 50 years? Because it's simple. It works with linear classifiers. It fits nicely into statistical models like the ones we saw in Lecture 4. And critically, nobody knew how to do better. Making up meaning-carrying vectors sounds impossible if you don't know the trick. Beat 2. 2003. Yoshua Bengio and colleagues publish a neural probabilistic language model. The paper is not really about embeddings. It's about predicting the next word in a sequence. But to do that, they had to represent each word as an input to a neural network. So they made every word map to a small dense vector, say 100 dimensions of decimals, and let the network learn those vectors during training. The magic. The network learned to make similar words land near each other in that 100-dimensional space. Because if cat and kitten appeared in similar contexts, the network needed similar predictions after seeing either, so it wound up placing them near each other geometrically. Similarity as a byproduct of the prediction task. Bengio's 2003 model was slow. It took weeks to train. Nobody outside the neural network community really noticed. But the IDA was live. A word could be a small, dense vector. Vectors could carry meaning. Everything downstream from word 12, Glove, Elmo, Bert, GPT traces back to that paper. 10 years before Mikolov's magic trick, the technique existed. It just wasn't fast enough to matter yet. Beat 3. What does distributed actually mean? Not just a dense, a specific mathematical property. In a one-hot vector, each dimension corresponds to a specific word. In a distributed vector, each dimension corresponds to some latent property, like animacy, or size, or formality. And any specific word is a mixture of all these properties. Important caveat. The dimensions don't have humantrpretable labels. The network doesn't announce in this dimension is animacy. We use animacy and size as metaphors when we look at what the trained vectors do. The actual dimensions are just whatever the network found useful for its prediction task. Distributed means each word lacks up many dimensions at once. Each dimension participates in representing many words. Overlap in both directions. This is why distributed representations are so powerful. In one-hot, if you've never seen the word RIZZ before, you have no information about it. In distributed vectors, if the network has learned that RIZZ appears in contexts similar to charm and confidence, the vector for RIZZ will end up near those other words. Generalization comes for free, which is exactly what Bengio 2003 was trying to solve. 3 takeaways before the quiz. 1. One-hot encoding. Each word its own dimension. 50,000 dimensions, every different word equally unrelated to every other. Fatal. 2. Bengio 2003 Neural Probabilistic Language Model. First real embedding, 10 years before Word2Vec. The idea was live, just slow. 3. Distributed representations. Each dimension a latent property, each word a mixture. Similar words land near each other. Generalization comes free. Quiz 1. In one-hot encoding, how similar is cat to kitten? A very similar, B slightly similar, C exactly as unrelated as cat and banana, or D depends on training data. C. Equally unrelated. That's the fatal flaw of one-hot. The dot product between any two different one-hot vectors is always 0. Distance is always the same. There's no room to encode in these two are related. All words look equally foreign to each other. Quiz 2. What did Bengio et al. 2003 actually publish? A Word2Vec. B. A neural language model that learned dense word vectors as a side effect. C. The Chomsky hierarchy. Or D. Glove. B. A neural probabilistic language model. The primary goal was next word prediction. Learning dense word embeddings was a byproduct of needing a numeric input. That side effect turned out to be the whole future of NLP. Quiz 3. Why do distributed representations generalize better than one-hot? A. They use more memory. B. Each dimension is a latent property. Each word a mixture. Similar words land near each other. C. They're written in Python. Or D. They're bigger. B. Overlap. In distributed vectors, each dimension participates in many words and each word activates many dimensions. If the network hasn't seen RIZZ but has seen charm and confidence, Riz still gets a reasonable vector because it lands in the same neighborhood. One-hot can't do this. Every word is isolated. Back to the puzzle. Bengio 2003 proved the idea works, but his model was too slow to be practical. 10 years later, 2013, Google's Mikolov figures out how to train dense word vectors in hours instead of weeks. And that speed unlocked everything. Next video, Word2Vec in detail. The 2013 earthquake. Next time, Word2Vec. Mikolov's 2013 paper. The 2 architecture trick, CBOW and skipgram. How Google made word embeddings 100 times faster to train, and why NLP research changed direction overnight. Hit subscribe.